Again, welcome. Today is October 20th. We are in week 9, actually. And today is chapters 16 and 17 together, and they all deal basically with two ideas. The first one is heat transfer. And there are three processes basically that takes heat from one point to another point, and they are conduction, convection, and also radiation. And then after that, we're going to talk about phase transition. Phase transition basically taking an element from one state to another state, solid to liquid or liquid to solid, liquid to gas or gas to liquid, and actually to some extent from gas to plasma state if you wish. Okay. So that is the topic of the day. So let's get into unless you guys have any question for me, I know I asked before the recording. So, and there are a couple of people who joined us after that. So, you guys don't have any questions, so we're going to get right into the material because this is quite long, basically stuff that we need to go through. As usual, we're going to focus just on the main points in here. This is 77 slides. I don't think that we're going to go through the entire number of slides. So I'm relying on you that you guys go through this material, you review the book, and if you have any questions, please do ask them, okay? And ask them in the discussion basically form, okay? Because you're accountable for all content in these chapters. So, as I said before, the chapter is divided into two components. The first one is heat transfer, and heat transfer occurs basically with three processes. The first one is the conduction, meaning that you have to have a material, usually metal, or a good conductor, to take heat from one point to the other. Case in point, for example, a spoon, which is made out of iron, basically, or at least steel spoon. If you put it near a source of heat, you're going to feel the heat come to the other side of the spoon. Now, in terms of practical applications, of course, we use it in terms of insulations. I mean, in hot weather, we would want the room or the car to stay cool. So what we do in this case, we turn on the AC. Well, heat will actually seek to the will leak, I'm sorry, to the outside environment, and we would want that to be insulated. So in this case, we really don't need good conductors, we need good insulators. Okay, so the opposite. So we would want to retain the heat in its place. And there are other applications, of course, of this process. And the other method also for heat transfer, and it has tremendous application on weather here on Earth, and that is convection. Convection is a process where basically a gas or liquid in general cools by basically rising from where it's hot to a place where it's colder and falls from where it's colder back to where it's higher and going into like a circular path. So at this point, for example, if I have a burner, under the burner, immediately on top of the burner, I have the liquid, for example, that is sitting on the pot, which is being heated. So that area there is a lot hotter than the top of the pot where there is a liquid basically is in contact with the air. The air is sitting at room temperature. So there is a gradient in temperature in here. So the hot side of the liquid will rise because its density is less actually, so it's lighter than the fluid around it, so it's going to rise, whereas the top of the fluid, which is colder, so therefore its density is higher, will fall. The process go in a circular fashion. This is basically how weather phenomenon, or at least the climate on Earth, basically operates. So this gives us an understanding of how climates work, but also in terms of what's going on, for example, in the core of the Earth, because actually the magma also has this kind of flow, albeit that's a very, very slow flow, relatively speaking, compared, for example, to the weather. And also that's exactly what's happening actually in the sun. The sun, between its surface and between its core, there is a huge layer of convection layer where heat is actually taken from the core of the sun, which is super hot, sitting at several tens of millions of degrees actually, to where the surface of the temperature a cool 5,500 Kelvin, basically, which is relatively, it's very hot compared to us in here, but relatively speaking, compared to the core of the sun is a lot less. So in this sense, those are the two processes that we're going to talk about. The third process is the process of radiation. Here is the deal with the first two. They need a medium. So that's the first topic of the discussion. Conduction and convection require a medium to transfer through. The first case of conduction, for example, a metal. Okay, heat goes from one end to the other side of the metal via conduction. So you need always a medium in that case. Without medium, you cannot have heat being transferred from one point to another. You're using conduction at least. Convection also requires a medium, a fluid of some sort. Okay, either liquid water or gas or some sort of a fluid where actually heat is again taken from a hot source to a cold source, and in this case density plays a major role. So in this case also you need a medium, whereas radiation does not require a medium. It moves from point to point in empty space. So that is the first point of discussion today. So the question is basically the difference between conduction and convection on one side and radiation is that radiation does not require a medium to move from point to point. Does this make sense to you guys? Point one today. Yes? I need some confirmation. Okay. So the difference, okay, Kyle, that's a good note in there. So the difference here is the prompt basically. What is the difference between convection and conduction on one side and radiation on the other side? Conduction and convection require a medium, whereas radiation can transfer in vacuum. Is this better now, Kyle? And everybody else, as a matter of fact. Okay, Amanda agrees. I would like you to put it in your own words. I don't want you to copy it, honestly. Okay, let me put it in a different word verbiage. Maybe it's going to help a little. Okay, we have three processes, correct? Two C's and one R: conduction and convection, and radiation. The two C's, conduction and convection, require something to travel through. They require material to travel through. Conduction require usually good conductor, and convection require usually a fluid of some sort, either a gas or a liquid. Radiation travels in vacuum, no matter. I mean, there is no need for any matter whatsoever. Better now? You could have, yes? Kyle, and everybody else too. Samantha agrees. Oh, okay, okay, everybody agrees. Okay, so that's prompt number one today. And then we're going to talk about Newton's law of cooling. Basically, this is something you know, okay? Either when we say cooling, it actually applies to warming also, okay? You have half cup of water and you have a full cup of, I'm sorry, probably it's not a good idea. Yeah, cup, okay, that's fine. And both of them are super cold. You get them from the refrigerator in the same temperature, and you let them in on the kitchen whatever table, for example. Okay, remember, one half of that, one half cup, and the other one is a full cup. You let them on the table, both of them, they come off the refrigerator super cold. You come an hour later, which one do you think is going to be warmer? The full cup or the half cup? Which one warms faster? Yes, very good. Same thing. Yeah, that's very good. That's how you're supposed to have it. I mean, a half cup, of course, you have less, so it's going to absorb more heat quickly, and then it's going to warm its temperature, whereas the full cup will take a little longer. And of course, if you take a bucket, for example, of ice versus if you take a spoon of ice, the spoon of ice will melt first before the whole bucket. That's the idea behind it. So that is one thing. The other thing also, if you take, for example, a cup of ice, frozen ice, full cup of it, okay, and you take it from the freezer and you put it in the refrigerator, and you take another cup, similar amount of ice from the freezer again, but you could put it outside in the sun. where it's super hot compared to the home. Which one would melt first? Which one will basically melt first? Is it the one sitting outside in the sun or the one in the refrigerator? Of course, the one sitting outside in the sun. Again, the gradient of temperature plays a role, and the mass also plays a role. That is basically what the law of cooling or the law of warming, as I said before. Okay, you would want to warm your cup of tea, full cup will warm, take longer to warm versus or to heat, for example, versus half of that amount. So that's basically the idea behind it. So two things play a role in this case: the difference in temperature in this law of Newton's law of cooling, and the other thing also is the amount of matter that needs to be warmed or cooled. Okay, so those are the two independent variables in this case. Okay. We're going to talk about global warming. Materials have different, their basically opacity or their reflection of light is actually frequency dependent. So what happened in this case is, and this is actually something you don't experiment with it because it's super dangerous. You can kill animals and people and things like that. And if you happen to be in a car, for example, during a summer day, heat is coming from the outside in the form of radiation. Radiation, in this case, is the process through which we're talking, and it comes in different frequencies, and mainly the visible light. That's why you can see from the other side of the window of the car, because visible light is coming so that you can see stuff from outside of the car. Now, once it's absorbed by the inside of the car, it heats the car from the inside, and the radiated energy now, which is again a form of heat being sent back, is not coming out in the visible region. Actually, it's coming in the infrared region, and the glass in that case is actually completely opaque for infrared. So in other words, light comes through as a form of energy, is taken by the car seat and everything else inside the car. When it's radiated, instead of leaving back through the window, it bounces off of the window because it's basically reflective for infrared, and heat is trapped in this case. So the longer the car stays in this state in the sun, the more heat accumulates inside the car, and the car will be hotter basically than outside the outside environment. So that is basically essentially what the greenhouse effect is. And it's used actually in greenhouses to grow food because the plastic plays the same role as glass. It takes radiation from the sun, especially in the winter, for example, when it's cold outside and it's not convenient for growing, for example, tomatoes and vegetables that require actually sun and heat to work, so, and humidity. So what happened in this case is the radiation from the sun, albeit it's less in the winter, comes through the glass. Once it passes through the glass or the plastic, then in this case it's going to be trapped because the soil warms, the plant warms, and try to emit it back, and when it's emitted, it emits in the infrared region. Now once it tries to go back through the glass, it doesn't, reflects back, and it's trapped. And that's how greenhouses are actually used for in agriculture. And this is the same thing that is happening with us here on Earth, because instead of having glass around the Earth, we have actually the atmosphere, and the atmosphere plays the same role as also as the glass. Radiation comes through in the visible region. It's trapped by the Earth. When it's radiated back with the basically the presence of CO2 and H2O, those two elements, they bounce the radiation back and trap the heat, and the Earth is hotter. And I don't think that there is anything more proof to that for here than here in Southern California. I think the last time we had any rain was sometime in the spring. So that is really a real thing that is happening, and this is essentially what that effect is. The second part deals with the phases of matter and basically phase transitions. Again, there are three main phases that we know at least on a daily basis here on Earth, and they are solids, liquids, and gases. The same material, water, for example, can go through all three stages. All you need to do is to change its temperature, raise its temperature, and it can go from being solid rock, ice, to melting. In this case, it becomes liquid, and it can survive there between 0 degrees Celsius all the way to 100 degrees Celsius. At that point, it's going to evaporate and become gas in the gas form. If you continue raising the temperature, though, what happened in this case, the water molecule first of all starts to dissociate, try to break, and then after that, actually the atoms start to lose their electrons. This is the so-called plasma state. Basically, you'll see flares going all over the place. But the thing with it is, at least in terms of the presence in the universe, it's mainly in the stars. The stars are in the plasma state. So all the stars, at least the ones that are going through their main sequence life, basically they're burning hydrogen in their core, they are actually in this state, the plasma state. Since a star like the sun, for example, represents more than 99% of the mass of the solar system, and we assume the same thing is at least true for all of the other stars in the universe, the plasma state is the most dominant form of matter in the universe. So it's not solids, it's not liquids, it's not gases. The main form of matter in the universe is actually in the plasma state, because of the fact that's how the state of all of the stars are. Okay. Of course, the processes of evaporation and the processes of condensation, those are reverse processes, and actually they're used in a sense, at least for living organisms, for animals specifically, as forms of basically discharging heat or getting cooler, basically trying to get cooler. We talk about the boiling and melting. They're all part of the phase transitions and energies and changes of phase. Basically, the energy required for melting ice, for example, and the energy required for boiling water. Okay, so that's basically part of the things that we're going to be talking about in this chapter. So we spent about 17 minutes, and I think we covered everything. We can go home now. We need some details though, okay? That's not good enough. Okay. Again, we talked about the fact that these are the three main processes. Let me see here. Do I have this drawing tool? Can I draw here? Yeah. So these are the first two C's, and this is the radiation in this case. That's the one that is different than the other two. Okay. Contraction is transfer of energy by electrons. So electrons are really the ones responsible for it. Remember when we talk about metals basically, let me stop sharing the screen and share with you another screen to show you how the metal would look like. So a metal is like any other, oops, I'm sorry, I'm not sharing that screen. I just basically turned it to myself, sorry. So imagine with me, I have a metal, and this is how it looks like. So I have a bunch of positive ions in here. Those are the basically the atoms or the nuclei, if you wish, plus the innermost electrons for whatever makes that element. So I have a bunch basically of atoms in here, and mainly they are positive charged because they're outer electrons that participate in the process of this electron. They can move freely, but you have enough of them so that they basically cancel. So the metal itself is neutral. If you don't believe me, pick up any metal. Do I have any metal? Yes, I have this. This is a metal. Don't ask me why I have it with me here. Okay. This is made out of metal. It's neutral. Case in point, I can touch it, and it doesn't do anything. This is another metal. This is actually made out of aluminum. So the same thing in here. I can touch it. It has no charge. So it's neutral. It has no charge. But it has, in like, for example, a piece of an insulator, like this rubber in here, which is really an insulator. The electrons are tightly connected to their ions, basically to their atoms, so they cannot really move freely. In here, they have the ability to move freely. That's why when there is a difference in temperature, when this is hotter than the other side, the heat can move via electrons. Okay, electrons will take the heat to the other side. Basically, they start to agitate to move the heat from one point to the other. Whereas in this case, it's very hard to do the same thing. So when you heat this point, actually, as a matter of fact, it starts to melt before you feel the heat on the other side, or you feel the heat through the air. Okay, so because this one is an insulator. So that is the process through which, because again, these electrons, they don't belong to their atoms anymore. They belong to the entire community of atoms. So the electrons in this model belong to the community of atoms. That is how matter you can think. That is how metals can you can think of them, and that's why they're good conductors. Because the minute there is a difference in temperature, the electrons can basically move that temperature from one point to the other point. The same thing when there is a difference in electrical potential, the electrons start to move freely. Okay, they're not being anchored to their atoms. However, when one of them moves to this side, this one, of course, will move to the other side. This one will move to the other side. And this one is actually replaced by another one. So there is always neutrality. So this state is always true for a conductor. Okay. Obviously, unless you can. Okay. We're not going to talk about the plasma frequency where you can actually create change the potential in here between this point and this point so that the electrons will not have enough time to replace one another, and then you have an ionized state in this case. Okay, but you have to do it so fast before the electron replace themselves that they will be non-neutral. So assuming that that's the case, we're not doing all conductors, even while doing electricity, they should be neutral. Okay. The only reason why you get electrocuted is because of the fact that you are completing the circuit. Okay. So we can stop sharing the screen. I just made my point through it. Because I think, and I agree, okay, at least one of you guys, I don't know if it's in this class or another class, mentioned the fact that it's probably not wise to keep on drawing on this thing. It becomes unreadable. So I'm taking your suggestions on that. Please do not. Oh, okay. Some of you are just doing the comments. So, good conductors conduct heat quickly, okay? And they include, for example, substances with loose electrons transfer energy quickly to other electrons to the solid. Good conductors are silver, copper, and other solid metals. Gold is actually one of the best conductors. Actually, it's better than silver and copper. Copper is used in the industry a lot because of its cheap, basically, because it's cheap. Silver and gold are not because they are more expensive. Okay, so and they both are better than copper. Copper is used in the industry, and actually, iron actually is a good conductor, but not as good. Actually, copper is about 10 times better, or actually 20 times better than iron. Okay, but iron will conduct also heat. Now, sometimes you're, like as I said before, you're not interested in conduction, you're interested in insulation. So you'd want to have an insulator: glass, wool, wood, paper, cork, plastic, foam, and air. Air actually is a good conductor, a good insulator. The only reason why heat transfers through the air is through another mechanism, not through conduction. Okay? Air transfers heat through actually convection. That's why air actually is, can transfer heat, but not through conduction. Same thing with electricity. Air is an insulator also of electricity. If air is a conductor of electricity, we have a problem, because all the power plugs that we have in our houses, they all have electricity in them. So if air is a conductor, then we will not be sitting in here and talking about it. Everything is electrified. Of course, given the right potential difference, they can conduct electricity. Case in point, lightning. Okay, all insulators, they can break. They have a point where you can break them, and they actually will conduct. Okay, so if you put a huge gradient of temperature, for example, along this insulator, it will conduct at some point. Okay, provided that there is, even in the vacuum, even when there is no air surrounding it. So if you heat it big enough, it's going to break. Same thing. If you put a huge potential difference, you will see sparks in that case too. Okay, and that's what lightning is. In general, wool, fur, and feathers, and that's what animals do actually in the winter, and because that's their good insulators because of the fact that they have air in them. Okay, this is an interesting question. If you hold one end of a metal bar against a piece of ice, okay, the end in your hand will soon become cold. That's daily experience. Basically, take your spoon, for example, and dip it in the ice and wait, okay? And you will see that after a while, your hand will become colder. You will feel the cold in your hand, okay? Does cold flow from the ice to your hand? Obviously, the answer is no, but can we understand why? Yes. The reason why you're feeling actually cold is because heat is being extracted from your hand. That's what Kyle is saying to the ice. Okay. Always think of it in terms of heat. So the only reason why you're feeling cold is because again, your 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 uh, your hand is actually losing heat towards the ice, and that's why the ice actually is melting too. Okay. Insulation. Okay, there is no perfect insulator, that is for sure. As much as there is no 100% perfect conductor of heat. And probably won't talk about electricity. We can talk about superconductors, but that's another story for another day. But at this point, in terms of perfect insulation, no. So that's why the power company, they always tell you, for example, to raise the lowest temperature in your, or at least their temperature in the at home when it's super hot outside, in order to save energy, so that there is energy for everybody to do what they need to do. Otherwise, everybody will lose power, including yourself. So if the temperature outside, let's say for example, is super hot, sitting at 105 degrees or 110 degrees as it was a few days back, okay, and you come to your AC unit and you lower it all the way to the minimum possible, which is, let's say, for example, I don't know, 60 degrees, 62 degrees. There is this much gradient in temperature between 110 and your 60 degrees, and your AC unit will work super hard trying to bring it to that low. Needs to consume a lot of power to bring it that low. If you raise the temperature, let's say, for example, 80 degrees, then the difference in this case is what? 110 minus 80, 30 degrees, versus if it was 60 and 110, that is 100, that is 50-degree difference, okay? So the AC unit does that, okay? So yeah, that's one problem. No matter how much good insulation you have in your home, because the AC unit is trying to basically get rid of the heat inside the house to the already hot outside. Okay, that's how AC units work. And but heat is still seeping. It's still coming to your house. One way or the other, even with the perfect insulation that you think that you have in your house, no matter how many, everything is closed, all the windows closed, everything has all of those perfect insulators around them, it's still okay. There is heat that is still coming from the inside, from the outside to the inside. As much as your AC is trying to remove heat from the already cold environment to the hot environment outside, it's still going to work super hot. So that is really a common sense. So there is no perfect insulator. That is no way. Even with this is with the conduction. We're not talking about any other mechanism. And the presence of convection, that makes things worse too, because heat will actually leak to the environment differently too. I mean, you will find other ways of getting out. Okay, this is because coal is a poor conductor. So if you walk fast enough, it's not going to transfer heat to your feet. Okay, I did not try it though, but somebody can try it and see if it works. At least people do it, at least who have the Convection, as I said before, requires a fluid of some sort, okay? Fluid that needs to circulate usually from a lower density to a higher density, okay? Because this one has a lower density because it's hot. It's immediately in contact with the burner where there is a source of the heat. So this bottom part in here is hot compared to the top part, which is in contact with the air, and it's actually evaporating there to extract more and more heat to cool down. So the temperature is less on the top than it's in the bottom. So the fluid is denser on the top than in the bottom. The bottom one, since it's denser, will automatically rise, and the one that is actually denser will fall. In doing so, when it rises, it takes heat with it, and it cools down. It becomes denser again, falls back, and so on and so forth. So that's basically a way to distribute heat and make heat work around the in the fluid in this case. So that is convection. Okay, it's the motion of the fluid itself that transfers heat. The fluid itself is moving, and it takes heat with it, cools down, and basically gets the temperature less. So it's going to get rid of the heat in this case, and becomes less dense and becomes denser and falls back, and so on and so forth in this cyclic rotations. Okay, and you can actually visualize it in here in this case. Usually when there is a big difference, you can actually see it too. Okay, and that's how the smoke actually you can see it too. Again, warm air expands, becomes less dense, and is buoyed apart. It rises until its density equals that of the surrounding air, and basically, okay, here is an experiment I want you to do, guys. Okay. Of course, you do this in the winter all the time, okay, and you probably are not aware of it. Try to blow on your hand with your lips basically not open, just like normal, okay? Okay. Versus if you bring your lips closer, you will feel that the air is different temperature. Okay. Do you guys notice that there is a difference between the two? At least how it feels. So when it's focused, what happened? Is it colder? The air feels colder or feels warmer when it comes out? Okay. It feels colder. Kyle is saying that the Dyson fans use that to. Okay, can you tell? I mean, does everybody agree or not? Did you guys try it or not? Everyone else. Okay. It's coming from the same area. So the source is the same temperature, but one of them feels different than the other. Does everybody, first of all, agree with Amanda, or she's by herself now? Okay. Everybody agrees with her. At least two more people. Okay, three. Okay. Can you now tell me why? Or should we leave that for later? That's the second point of discussion. Okay, that's the correct answer. Okay, because it expands. While it expands, in this case, it loses the heat, so it feels cooler. Okay. Yes. So that's a way for you to actually. That's how actually what's going on in this situation too. Okay. So this is the cooling by expansion. That's exactly how what happened in here when you blow with your hand. So the answer is exactly how you guys stated. And that is the second point of discussion today. We need to move a little faster because we have quite few and we already consumed half an hour. But the half an hour was good because we spent the entire, basically first part of it just discussing the entire thing. which is basically the entire chapter. So I feel good, even if we finish the chapter now, that you guys should be able to do okay. So again, this is basically how you can understand the weather, at least near the beach. I think we talked about this one sometime before, and that you will feel during the daytime because there is a big difference in temperature between the inland. Remember, the specific heat of water is so high that its temperature doesn't change that much between. I mean, when the sun, for example, is high up. So if it was during night 64 degrees, and the sun is just midday, it's not going to rise except probably by a degree. Whereas the land, in this case, because it has low specific heat, in this case, is going to heat up faster. And now the air is denser on this side because it's lower temperature than the air on this side, which is supposed to be hotter. So it's higher. So the density in this case is less. So the air starts to rise in this case in order to cool down. Once it cools down, it's going to fall again, and then it's going to follow the circulation in this case. Okay. Because the temperature in here is supposed to be a cooler than the temperature up, which is hotter. So that's why it does this pattern. Okay. At night, it's the opposite. Because again, for the same reason, the specific heat is lower for the case of soil and sand and earth than that is of water. Water mainly doesn't change much temperature. So in this case, the process is reversed, and the smoke actually will see it going toward land during daytime. During nighttime, you will see that the bonfire will move toward the sea. Did any one of you participate in a bonfire or at least notice something similar? Before COVID, I know COVID now doesn't allow bonfires, at least near the ocean, near the sea. No? Nobody? Okay. Very good. At least a couple of people did. Okay. Radiation is the third process basically that we're talking about, transfers energy from the sun through empty space. The reason why is if it were not for radiation, we would not have enough energy on the earth. The source of heat on earth is coming from the sun. There is some that is coming from the core of the earth, but the main source is actually coming from the sun. And there is empty space between the earth and the sun. And that's how radiation travels between the earth and the sun. Okay. As a matter of fact, also radiation is coming from different stars. Stars are very far, where is basically empty space between us. There are tens, sometimes hundreds and thousands of light years between us and stars and the Milky Way galaxy, and yet we see them. And how do we see them? It's through radiation, the light they emit. We can see them, we can detect the radiation. As a matter of fact, light is crossing the entire universe, crossing billions of light years from further away galaxies. We can still see them because of the same thing, that radiation travels through empty space. Okay, that is another way for heat also to escape, because radiation, I mean heat, what we associate with it, heat is just certain form. It's an energy, of course, and the energy associated with electromagnetic radiation is actually also can be in the form of heat too, in the infrared region. But other forms of heat, for example, other forms of radiation, they don't seem hot to us, but they carry energy nonetheless. Okay, and they're actually more energetic than the infrared, than what we call heat. Okay. Again, the earth radiates heat. Anybody radiates heat. Anything radiates heat. As long as they have temperature, they have heat. So when your significant other that tells you that you're radiating today, he or she is not wrong. And because everybody does. Okay. That's what we use goggles for when we try to see living creatures at night, because they radiate heat. Albeit the frequency that we emit is not in the visible range. So during nighttime, you cannot see a person or an animal with a naked eye. But with a device that can basically detect infrared radiation and transfer it to a visible so that you can see it, you can actually see that animal or that person. Okay. Which body glows with the electromagnetic waves? The sun, the earth, and everything else, as long as that has temperature. Everything else radiates electromagnetic radiation. You and I and everything that is sitting in this room, all of them, they emit radiation because of the fact that they have temperature. Okay? So this is a basic concept in here. So it's basically what we call the electromagnetic waves, okay, the EM waves. And that includes the infrared, the one that we feel as heat, and anything else also in there too. You have the super shortwave radiation, which is extremely energetic. It can cause cancer, it can kill you, gamma radiation, actually, right on the spot. X-rays are also super energetic, and they are also a form of electromagnetic radiation. They can kill animals and they can kill people, especially with high enough doses. Ultraviolet, they can cause cancer and they can destroy or can wreak havoc on life in general. It will not sustain for a long time with the infrared with the ultraviolet. Violet and the visible is what we see. Then you have the red, and then you have the infrared. The infrared is what we associate with heat because it's associated with the motion of the molecules, and that is basically heat. The microwave uses infrared. The microwave in the kitchen uses infrared to basically agitate the water molecules inside the food, and that's how heat is actually transferred from electromagnetic radiation to heating or cooking, actually, in that case, without resolving to a fire or anything like that. Okay, so it's directly using radiation. And like, for example, the oven, which is the burner using electrical process, it uses actually a resistor. And the resistor in this case is a process of actually getting heat also transferred to the environment. But the microwave itself uses this principle, radiation, pure radiation. Okay, in specific frequencies though, because you would want the water to agitate enough so that the heat is transferred and trapped in there so that you take the food from the microwave and you can eat it. Okay. Again, radio waves is also another one, but radio waves are much, much less energetic. At least we don't feel them as heat. Okay. And so on and so forth. The concept of wavelength is associated with all waves, including in this case electromagnetic radiation. The infrared happened to be in a specific wavelength region, which is a few centimeters and millimeters. That is basically the one associated with the agitation of the molecules. Here is what I was talking earlier about the fact that anything and everything emits radiation. Given a high enough temperature, this curve in here explains that. Okay. At T equal to 3200 Kelvin, remember I said earlier the sun is about 5500 Kelvin. Okay. And that's what makes it in the visible region. Okay. That is the sun. And that's why we can see it in the visible region. I don't know if we evolved to see that, but that is basically what the temperature of the sun is. For a star that is a lot less heat in it, it's not going to appear visible because this is the visible region in it. And this is the frequency, okay? It's peaked for lower frequencies than that, okay? It's peaked for a lot less frequency than this. So it's peaked in the infrared region. We're not going to see much of that star at all, okay? And then comes a little bit of other frequencies. Temperature that is 2400 is even less, so it's peaked less. This is typically not a star, okay? This could be something that is a decaying star from an old time, or some planet super hot like Jupiter-like planet or something like that. 1600 Kelvin. Again, you can take a metal and heat it up, and you will see the same thing. When it's getting hotter and hotter, you can still see the color of the metal. But by the time it reaches a certain temperature, its temperature starts to change. Now it's going to be red, which is the first frequency you're going to see. And then it's going to get shift in frequency until it becomes yellow. Okay? If you keep it warm and doesn't melt, and don't do this experiment at home, it's super hot. You need extreme high energy temperatures. Okay? And then it becomes white. At that point, you have all frequencies involved. Because white color, you have the violet, the blue, and the green, and the yellow, and the orange, and the red, and everybody involved in that point to get to the white color. Okay. If you increase it so much, and you can do that on Earth, at least you may do it in the laboratory for a short period of time, but you cannot do it outside, then the temperature probably will shift toward the green, and then toward the blue, and then toward the violet, and then to places where you can't even see the color. It becomes black again because it's so energetic, so much energy. And by that time, most metals on Earth will melt. Okay, everything will melt at that temperature that we know of. On the surface of the temperature, where everything is melting, remember the temperature is 5,500 Kelvin, and the sun appears yellow, not even white, because it's not hot enough for this process to reach the white level. A star that looks bluish, that means it's super hot. It's much more than this. Maybe 10,000, maybe 15,000. Some of them, they appear about 25,000 Kelvin, and case in point, Sirius star. Okay, so the temperature determines the color, really. And the only reason why we are not basically in the visible region is because our temperature is much less. We are sitting at 300 Kelvin. So right now, our curve would look like this, probably here. Barely here at 300 Kelvin. But we have a curve nonetheless. We emit radiation still. Again, the longer the wavelength, the cooler, the less energy it carries. The higher the temperature, the higher the frequency. Okay. This is basically what we're saying in here. Okay. This higher temperature will appear at a higher frequency. Less temperature will appear at less frequency, and so on and so forth. Here is the peak frequency, the one I'm talking about. Here is the peak frequency. Here is the peak frequency, and here is our peak frequency. So the peak frequency shifts toward lower and lower with less and less temperature. Okay, so that's exactly what we're talking about. Remember, frequency and wavelength are opposite to one another. The lower the frequency, the longer the wavelength. So this is actually cooler than this one. Okay. Materials absorb and emit radiation. Basically, a good observer is a good emitter, okay, of radiation. And they take radiation and they absorb it, basically, at least, and the atoms will be excited in there, and the molecules will be excited, and then they will emit it back, okay, in order to go back to their ground state when they cool down. Again, good absorbers are good good emitters too. Okay, and poor absorbers are also poor emitters. And okay, let me, because dirty snow in this case will absorb more heat, so it's going to melt faster. Let's get to some important concepts in here. The black body radiation explains basically the process in here of how absorptions work. So to get to the Newton's law of cooling, this is, I already mentioned how this law works basically. It depends first of all on the gradient of temperature, difference in temperature, delta T. Think of the process of taking, for example, an ice cube and put it in the refrigerator versus an ice cube and put it outside in the sun. Obviously, the change in temperature going from the freezer to the outside is much higher than taking it from the freezer and putting it back in the refrigerator. Therefore, the one that has the higher delta T will melt faster. Okay. And also depends on the amount of matter too. Here is the greenhouse effect I was talking about. So again, short wavelength, higher energy in this case, are absorbed, and they are transparent as far as, I mean, the glass is transparent as far as this radiation. In other words, Uh, that's how you see stuff through glass anyway, because the fact that visible light is the glass is transparent for visible light. Now, the material in this case, the flower and this, the ground and everything absorbs this radiation. Now it absorbs it, it's excited, it emits it back. When it emits it back, it emits it through stages. The energy levels in an atom are through different energy levels. They are not all evenly spaced. So what happened in this case, you excite it with super high energy because the visible light is high energy. Now it's excited in here. So in order to go back to the ground state, it doesn't go back to the same stage. It goes back through stages. So here, it's less energy that is emitted, meaning it's longer wavelength. From here to here, it's also less energy that is transmitted, and it goes through shorter, longer wavelength. And in here, it's less frequency that is emitted, meaning it's shorter wavelength. Longer wavelength. Remember, less energy, longer wavelength. So the wavelength that comes out in here, which is usually in the infrared region, is the glass is opaque as far as that. It's not transparent anymore. So it's going to reflect it back. It's going to be absorbed again by the material, but instead of being excited all the way to these energy levels, depending on the frequency, so it could be excited to here or here, for example, only. So the second time, when it's going to transmit it, it's going to again transmit it in the infrared. Meanwhile, continuously, the material is taking the longer wavelength and getting excited here and here to that level. And the radiation now is trapped in here in this cycle. So it's not going to go all the way back to where we were in the original point. So that is really how this process works in here. And that's why, as long as the material is still exposed to the radiation, it is going to have that trapped heat. Okay. So even at night, it's going to have trapped heat. Of course, we said that before, that conduction also transmits heat. So ultimately, it's going to cool down because of conduction. Even though glass is a poor conductor, it's actually an insulator, it's going to let heat escape at some point. And the ground also will let heat actually escape through the embother side. And ultimately, it's going to cool down after a long period of time. That is actually for the greenhouse, the one that is used in the agriculture. But for the Earth, it's a different story altogether. You have to wait for a long, long time before the process is reversed naturally if we're still not putting more greenhouse gases in the atmosphere. Okay. So this is the one that we're talking about. This is a real effect, by the way. This is not political thing. Okay. There are studies that support this one with the increased, basically with the advent of technology, more and more basically burning of fuel. Carbon-based fuels and all of that. Carbons and greenhouse gases are released, and the temperature actually in the entire planet is increasing because of that. Unless we do something about it, I don't think that this is going to be good for our civilization altogether. There is data that support this one, so this is not some political thing. I know that some people what they want to say, but that's not the case. Okay, forms of solar energy again. Earth receives per the hour, okay, per second actually, 1,400 joules per meter squared. So if you have, for example, if you go, for example, in your pool, I don't know how many meters squared that it has, at least the surface, you're going to receive that much heat on a regular basis. So you can take that heat and convert it into energy. But there is another way of actually taking the energy, which is 400 watts per meter squared, and that is using the solar panels. The solar panels actually makes electricity directly through that process, okay, using the so-called photoelectric effect. And I think we have that effect down the road. We still have about, a few minutes. Phase transformation. Again, we talked about all of this in the introduction, so I'm hoping that you guys will go and revisit these things. And if you have any questions, please let me know through these things, because again, the three main solids are, or at least four solids in here, they're listed: solid, liquid, gas, and plasma states, okay? Before you reach the plasma state, you have to go through an ionization, basically, process. Dissociation process first. Again, By increasing the temperature, you go through this side. By decreasing the temperature, you reverse the process. The evaporation in this case, you are sitting right at the point where like for example, liquid water at 100 degrees. So in this case, the water molecules that are the water basically sorry, yeah, the water molecules in this case that are bound by some chemical bonding, which are related to the fact that the water is actually a polar molecule, they actually receive enough energy and they're taken outside of this region, and they are moving faster now, and they are becoming in the vapor state. Others, they condensate backward, basically losing some of that energy. So this is the equilibrium point in here. We are going through a phase transformation in this case through the evaporation. The condensation is the reverse of that. Evaporation is a process basically of cooling down in the animal kingdom, including gas. That's why we transpire, okay? We get rid of the heat and we cool down using that process. Sublimation is a phase transition directly from solid to gas, okay? Dry ice, for example, can do that. If you have had dry ice, which is in the ice form, and you basically pour in it water, for example, and then boom, it's going to move to the gas state. And that is CO2, carbon dioxide. Condensation, as I said, is the reverse process of the evaporation. And this is how you feel cold when you step out, because you are losing actually, in this case, the condensation in this case. I'm trying to move faster a little bit. The boiling again. We explained this one earlier when we were talking about the convection, because in this case, the boiling again, the density starts to become less and less of the gas, and that's why it rises. Okay, and this is the bubbles that start to form during the boiling process around 100 degrees Celsius. What else in here that we need to do? Okay, all of these processes require energy, as I said before. If you go from a solid ice sitting, for example, at negative 10 degrees Celsius, and you raise its temperature from negative 10 degrees Celsius to 0 degrees Celsius, at that point, all the heat in this case is just raising ice, still have ice. But for you need, depending on the quantity of ice, you need, in this case, amount of energy to melt it, okay, to have liquid water. So during that stage of phase transformation, you still have water and ice basically coexisting with one another, one of them moving to the other state until all of the ice is melted before the ice temperature starts to change, okay? Okay, I know we're running a little bit out of time, so I'm going to leave the rest with you guys. Unless you have a question, I want to just get to a point in here before it's too late. So far we have 2 points of discussion. Yes or no? Yes? Okay, so I think that's enough for today. I think the questions are good enough to cover these materials, okay? Please watch for the assignments. I know we had an exam last week and I promised not to put a lot of assignments after that, but we still have homework that needs to be done. And I know already mentioned the 3 problems from the previous chapter that needs to be achieved. So there will be those 3 plus from these 2 chapters. Good? So I'll see you guys on Thursday. And watch for Canvas for those assignments. Any questions? No? I'm going to stop the recording then.